Hello again, and welcome to our final lecture on limits. Last time we talked a lot about limits and discussed the concept of continuity, and we even did an application with the intermediate value theorem. Today we're going to look at some really interesting behavior of functions. We'll first look at something called infinite limits. This will be functions that grow without bound or decrease without bound. They go off to infinity or to minus infinity. And then we'll also look at the concept of limits at infinity. Now that means what happens to a function as x gets larger and larger or as x gets smaller and smaller towards negative infinity. So both of these concepts are related to each other, and we'll deal with each one in turn and see some applications of them. Let me begin with an example, as I usually do. Let's look at the function 3 over x minus 2. Here's a graph of that function. This is the graph of 3 over x minus 2. Now, look what's happening according to the graph as I get nearer and nearer to 2. From the right, as I get nearer and nearer to 2, the function seems to be growing, getting larger and larger. Whereas from the left, it's getting smaller and smaller. You would say that it's going down to minus infinity informally here. So the line x equals 2, that vertical line, is what we call a vertical asymptote. The function is not defined there. 2 is not in the domain. And that vertical line is not part of the graph. That's called a vertical asymptote in the sense that the function gets closer and closer to the line x equals 2 as it goes off to infinity or minus infinity. So the notation for this is as follows. We say that the limit of the function f of x as x approaches 2 from the right, so that's the 2 with the little plus sign above it, is infinity. And as x approaches 2 from the left, and that's the little minus sign, is minus infinity. These are what are called infinite limits. The limit doesn't exist there. Let's be careful. I'm not saying the limit exists, because that's not a number. Infinity's not a number. We're just describing the behavior. Okay, and again, x equals 2 is a vertical asymptote. Notice again how we're using one-sided limits here, approaching from one side alone. Let's look at another example. How about 1 over x minus 1 quantity squared? Well, let's approach 1 from 1. So x approaching 1 of 1 over x minus 1 squared. Again, it's not defined at 1, so something strange is happening there. And analytically, as I get closer and closer to 1, x minus 1 gets closer and closer to 0. And that means its reciprocal, 1 over x minus 1 squared, is blowing up. It's getting larger and larger, isn't it? So 1 over x minus 1 squared is a large positive number when x is very close to 1. So we say that the limit, as x approaches 1, of 1 over x minus 1 squared equals infinity. Again, we aren't saying the limit exists. The limit does not exist, but we're describing the behavior of the function as going off to infinity. Here's a picture of that graph. The function, as you see, at 1 is not defined, but it's getting larger and larger as I get closer and closer to 1. The line x equals 1 is a vertical asymptote of this graph. Now, here's a common pitfall I want to make sure we understand, and I've said it a few times already. When we write the equal sign, like limit as x approaches c of a function f of x is infinity, that does not mean that the limit exists. On the contrary, this tells us the limit does not exist, but rather it describes the behavior of the function. It describes that unbounded behavior of the limit. So infinity is not a number. Just keep that in mind. It's not a number, but it's describing the behavior that it's getting larger and larger. Good. Now, I've used the word vertical asymptote a few times. Let me give a more formal definition of it. We say that f of x approaches infinity or negative infinity, as x approaches c from the right or left. And if that is happening, then we say that the line x equals c is a vertical asymptote of the graph of the function. So you're a vertical asymptote if the function is getting closer and closer to you by going off to plus infinity or minus infinity. Vertical asymptotes occur at points x equals c where the function is not defined. Okay, the function's not defined at its vertical asymptote, but it has that strange behavior that is getting closer and closer to its vertical asymptote. Now let's go back to our old friend, the tangent function. We've seen it a number of times already. Let's talk about its vertical asymptotes. Well, remember what the graph looked like. Here it is. It has these periodic pieces, don't we? You see these chunks of this tangent function. Let's say focus at pi over 2. The function's not defined at pi over 2, is it? It's not defined there. But look at the behavior near pi over 2. The limit from the left is plus infinity, and the limit from the right is minus infinity. So pi over 2 is a vertical asymptote of the tangent function. How many vertical asymptotes does the tangent function have? How many? Well, an infinite number. Wow. It has lots of vertical asymptotes. Pi over 2, 3 pi over 2, 5 pi over 2, and then the other way, minus pi over 2, minus 3 pi over 2, etc. And you see that we have these one-sided limits. On one side, the limit's plus infinity, and on the other side, the limit is minus infinity. I'd like to show you now a little bit trickier problem. It's kind of fun. You'll like this one, I think. Let's look at the function x squared plus 2x minus 8 over x squared minus 4, and let's find its vertical asymptotes. Now, one of the natural things to do is to say, well, it'll have this unbounded behavior when the denominator is 0. So you might think, I'll just factor the denominator, x squared minus 4, and that'll give me my vertical asymptotes. You got to be careful here, and you'll see why in a moment. Let's look closer at this function and to see what's happening. So I'm going to do some algebra on this function, this kind of algebra we've used before. We take our original function and factor numerator and denominator. The numerator factors to x minus 2 times x plus 4. The denominator factors as the difference of two squares, x minus 2 times x plus 2. And oh ho, there's a common factor. The x minus 2's cancel each other, and I've simplified it to x plus 4 over x plus 2, as long as I remember that x does not equal 2. Okay, what do we observe here? The original function equals this new function, x plus 4 over x plus 2, except it has a hole at x equals 2. These two agree everywhere except at the point x equals 2. So I ask you, is x equal 2 a vertical asymptote? Well, no, it's not, because 2 is a factor of both the numerator and the denominator. At 2, the function's not defined, I admit that, but the function is well behaved near 2. What does it want to be near 2? What is it getting near? It's getting near 2 plus 4 over 2 plus 2, or 3 halves. Isn't that interesting? 2 is not a vertical asymptote. Now, minus 2 is, because minus 2, the denominator vanishes and the numerator does not vanish. Here's a graph of that function. That's the original function we talked about in this example. Notice that it looks just fine, except when x is 2, there's a hole in it. And I've indicated that, a little hole there. You could fill that hole in. That's a removable discontinuity. It wants to be 3 halves if it's going to respect its limit. But 2 is not a vertical asymptote. Look, it's not going off to infinity there, is it? It's perfectly well behaved. But over at minus 2, you see that it's blowing up to infinity or down to minus infinity. So this is a common pitfall. To find the vertical asymptotes, you can't just find the zeros of the denominator, because some of those zeros might also be zeros of the numerator. So you got to make sure you cancel like factors in your problem before you determine those vertical asymptotes. And as usual, I encourage you to do a verification with your graphing utility to check out some of these results of vertical asymptotes. Let me show you an example here of vertical asymptotes, an example to relativity theory for our physics folks. According to the theory of relativity, the mass m of a particle depends on its velocity, and it's given by the following formula: m equals m sub 0, m sub 0 is the rest mass of the particle, divided by the square root of 1 minus the quantity v squared over c squared. V is the velocity of the particle, and c is the speed of light. So, I ask the following question: what happens to the mass m as the particle's speed gets closer and closer to the speed of light? So we're asking what happens in the limit as the velocity v approaches c from the left, from values below the speed of light. Well, look what happens. It's pretty easy to see. As v gets closer to c, v squared over c squared gets closer and closer to 1. The denominator gets closer and closer to 1 minus 1, or 0. It's blowing up to infinity, isn't it? And so you see from relativity theory that as a particle velocity increases, its mass also increases. Isn't that interesting? So now let's turn to the other type of limit I'd like to talk about today, and that is limits at infinity. Again, I'll begin with an example. Let's look at the function 3x squared over x squared plus 1. Here's a graph of that function. This is 3x squared over x squared plus 1. Well, look at the curious behavior as x gets larger and larger. It seems like it's getting closer and closer to y equals 3. And the same is true as x goes in the negative direction. It's getting closer and closer to 3. We like to say it in the following way. As x increases without bound, that means you go out in the x-axis, really big values of x, then the function approaches 3. And as x decreases without bound, f approaches 3. Here's how we write that mathematically. We say that the limit as x approaches infinity, so you put the x approaching infinity down underneath the limit symbol, of the function equals 3, and the same is true as x approaches minus infinity. We say here that y equals 3 is a horizontal asymptote of the graph. The technical definition of horizontal asymptote is as follows. We say that a line y equals L, a horizontal line y equals L, is a horizontal asymptote of the graph of a function if the limit of the function as x approaches minus infinity is L, or as x approaches infinity is equal to L. Good. Let's look at some examples. What I'd like to do here is look at a series of polynomials that almost look alike, and to get a real feel for this horizontal asymptote behavior, in other words, the behavior out at plus and minus infinity. So these three examples almost are the same. The first one is, well, they all have the same denominator, which is 3x squared plus 1. It's the numerators that I'm changing. The first one is 2x plus 5, the second one's 2x squared plus 5, and the third one is 2x cubed plus 5. Let me first give you an intuitive analysis of what these limits will be, and then we'll go ahead and do them algebraically. How about that first one? What's the limit as x goes out to plus infinity, x gets larger and larger, of 2x plus 5 over 3x squared plus 1? Well, here's the intuitive argument. If x is really big, the plus 5 and the plus 1 are irrelevant. When you're dealing with numbers like a billion or a googolplex, those numbers are just buried. They don't import. And now what about the numerator? It's 2 times a big number, and the denominator is 3 times a big number squared. So the denominator is getting bigger much faster than the numerator. I would suspect that that limit will be 0 because the denominator's getting much bigger than the numerator. It's winning the battle. How about the second one? Now the numerator's 2x squared plus 5, denominator's 3x squared plus 1. Again, when I'm dealing out there with large values of x, the plus 5 and the plus 1 are going to be essentially irrelevant. And I'm dealing with 2 times a large number squared over 3 times a large number squared. Those large numbers will cancel each other, and I'm left just with 2/3. So my guess is that second limit's going to be 2/3. In a moment, I'll prove it for you. How about the third one? Well, I think you get the picture, don't you? The third one, it's the numerator that's now bigger than the denominator. It's 2x cubed plus 5. And so that one we suspect will blow up to infinity. It will get larger and larger. So let's do the algebra now to verify those results. You'll see that the trick's the same each time. Let's look at the first one, 2x plus 5 over 3x squared plus 1. Well, multiply numerator and denominator by 1 over x squared. And watch what happens when I do that. The 1 over x squared slides in to multiply times 2x plus 5, and so the numerator simplifies to 2 over x plus 5 over x squared. How about the denominator? It simplifies to 3 plus 1 over x squared. So I've multiplied the numerator and denominator by 1, by the same quantity, and hence I get a new expression. And now imagine x going to infinity. The numerator will go to 0. 2 over a large number and 5 over a large number all go to 0. But what about the denominator? It's got a 3 down there. So the 3 is solid. It doesn't move when I take the limit. And hence the resulting limit is 0 over 3, which equals 0. Which, again, we did that intuitively a few minutes ago. Let's look at the second one, which had that interesting answer of 2/3. Again, I start with the original problem and do the same trick. Multiply numerator and denominator by 1 over x squared, and then slide that in with some algebra, and you get the following expression. 2 plus 5 over x squared, all divided by 3 plus 1 over x squared. And now let x go to infinity. The 5 over x squared, poof, it goes to 0. The 1 over x squared in the denominator, poof, it goes to 0, and we're left with 2 over 3. Our answer is 2/3. And the third one, I think you get the picture. I invite you to do this on your own, but you'll see that in this case, the numerator wins the battle and the function gets larger and larger, and we say that the limit is infinity. That is to say, the limit does not exist, but it does not exist in a special way. The function is getting larger and larger as x gets larger. As usual, I invite you to verify all of these limits with your graphing utility, and you'll see that the graphs correspond to what we just did. Now, let's step back a bit and summarize our results for these quotients of polynomials. Quotients of polynomials are often called rational functions. Polynomial divided by polynomial. What did we observe? Well, if the degree of the numerator is smaller, less than the degree of the denominator, the limit's 0. If they have the same degree, then the limit is the ratio of the leading coefficients, that 2 over 3. And if the numerator is bigger in degree, then the limit's going to be either infinity or perhaps minus infinity. So that's a nice rule to keep in mind. Well, my students often say, Professor, why don't we just use calculators in this class? They can answer all the questions for us. We don't need to do any thinking. Just let the calculator do the problem. Well, let me show you kind of a curious example. Let's graph this wild function on a graphing calculator. Here's a picture of it. And notice the screen that I'm using here. X is between minus 10 and 10, but the y values are between minus 2 and 2. And if you were to look at this graph, what would you think the limit as x approaches infinity or minus infinity is? What are the horizontal asymptotes? You would think perhaps it's 1, wouldn't you? Because look, it's going closer and closer to 1 as I go out to the right or to the left. But wait, look back at the function. This is a rational function, polynomial over polynomial. And the leading coefficients are 2 for the numerator and 1 for the denominator. So the actual answer should be 2. You see, the graph that I've shown from -10 to 10 doesn't really show the true behavior. You would have to take a screen that is really gigantic, something that's unnatural to do, in order to actually realize that the horizontal asymptote is y equals 2 rather than y equals 1. So these calculators can fool you if you aren't careful. We've seen an example of a function with, well, up to now, our functions have only had 1 horizontal asymptote. Let me show you a curious example of a function with 2 horizontal asymptotes. How about 3x over square root of x squared plus 2? Okay, look what's going to happen here. As x gets larger and larger positive, you can sort of say, well, that 2 in the denominator is not going to be very important. So it's like 3x over the square root of x squared, which is the same as 3x over x, and that's about 3. So the limit to the right, the limit as x approaches infinity, is going to be 3. How about approaching negative infinity? The same kind of argument, but now there's a little kicker here. The numerator is going to be negative, because I'm approaching negative infinity. The denominator is always positive, because the square root of a number is always non-negative. And so now it's going to be -3 to the left. Here's a picture of that function. Kind of looks like the tangent function kind of twisted around, but it's not. This is a rational function. This is a square root type function. But notice that off to the right, it's approaching 3, and off to the left, it's approaching -3. Kind of interesting, isn't it? Let me show you an example now as applied to biology. Here we're going to model the level of oxygen in a pond. And we'll call 1 to be the normal level, 100% oxygen at the unpolluted time. And then the model that, say, we come up with when we measure pollution in ponds is t squared minus t plus 1 over t squared plus 1. In real life, models would be much more complicated than this, but the principles are just about the same. So somebody dumps some organic waste into the pond, and so the level of oxygen is going to go down. For instance, after 1 week, the level of oxygen is F of 1, and if you plug 1 into our model, you get that it's 1/2 or 50%. So the level of oxygen is now 50% of what it used to be. And at time 2 weeks, it's 60%. And at time 10 weeks, it's 91 over 101, or about 90%, 90.1 to be more exact. So what's happening here? What is going to happen as t approaches infinity? What's going to happen to the level of oxygen? Well, look at the original model. It's a polynomial over a polynomial. They have the same degree, 2. And so the leading coefficients, it's that ratio, 1 over 1. So ultimately, as a limit, the horizontal asymptote will be 1, or 100%. Here's a graph of this model. Notice that at time 0, the function is equal to 1. It's got the full amount of oxygen, 100%. And then somebody throws this stuff in, and the model shows that the amount of oxygen goes down, and I've put some dots there at 1 and 2, which we calculated. But notice the function comes back up, and it approaches its horizontal asymptote. Here's a problem that I do in all my lectures. This is kind of a problem that brings back a lot of the limit ideas, kind of summarizes many, many limit ideas that we've seen in this lecture and the previous 2 lectures. I like to call on students for this. I won't call on you, of course, but here's what I tell them. I give them a problem, and I see if they can give me an answer. And here's the problem I'll pose. Suppose I give you a function and the value at 2 is 4. So suppose f of 2 is 4. That's all you know about this function. F of 2 is 4. What can you say about the limit of this function as x approaches 2? So I give you the value at 2, and I ask you what is the limit as you approach 2. And so I'll ask my students that question, and hopefully they'll say, Professor, you can't say anything. You don't know what's going to happen in the limit sense just because you know the value at the point you're approaching. That says nothing about the limit as you get nearer to that point. Remember the hiccup function? As I approached 2, the limit was 1, but then there was a hiccup and the value was something else. So the answer to that question, it's kind of a trick question for my students. The answer is nothing. You can't say anything, Professor. And then I ask a reverse question. Suppose you know the limit as x approaches 2 is 4. What can you say about the value at 2? And again, my poor students have to answer. I call on somebody, and hopefully you'll agree with the answer that you can say nothing. You can't say anything. Just because the limit is 4 as you approach 2, that says nothing about the value at 2. In fact, it might not even be defined at 2. Now, that said, the reason this kind of confuses students and me sometimes, people think, well, if the function's continuous, if the function were continuous, then all these answers would be different because it would respect its limit, wouldn't it? You would be able to say something. But if the function is just an arbitrary function, you have no idea what it is, you can't make any judgments there. Let me ask another question, which I like to do in class. In life, it's a real life question. How many vertical asymptotes can a function possibly have? In other words, is there any rule about the maximum number or minimum number of vertical asymptotes that a function can have? What do you think? Well, the answer is basically any number you want. There are functions that have no vertical asymptotes, or 1, or 2, or 5, or 10. In fact, there are functions that have an infinite number of vertical asymptotes. You remember which it is? Can you think of an example? How about the tangent function? It has an infinite number of vertical asymptotes. Can you think of another one? How about cotangent? That too has an infinite number of vertical asymptotes. Isn't that interesting? Well, let's pose a related question. How many horizontal asymptotes can a function have? What do you think now? What do you think now? Well, you could have 0. For instance, the function, let me think, how about y equals x, f of x equals x, the straight line of slope 1. It has no horizontal asymptotes. You could have 1 horizontal asymptote. We've had lots of examples of that. You could even have 2 horizontal asymptotes, couldn't you? And we saw an example previously of a function with 2 horizontal asymptotes. One of them was out to plus infinity, it had a certain value, and then out to minus infinity, it had a different value. It had 2 horizontal asymptotes. Could you have more? I think not, just because there are only 2 limits to take. One is x to plus infinity, so at most there'll be 1 limit there. That'll be one of the horizontal asymptotes, and then going to minus infinity will be the other one, and that's it. At most you can have just 2. Good. Well done. So, we are pretty much finished now with our study of limits and asymptotes. I'm the first to admit, it's kind of difficult material. It's interesting. Hopefully it's been a challenge to you, but you have a good feel now for calculating some limits and some asymptotes. Don't forget we have a workbook where you can practice your limit skills. Next time, we'll use limits to go back to that tangent line problem and develop something called the derivative. We will generalize that example I did in lecture 1 of the tangent line to a parabola. So I'm looking forward to seeing you next time when we begin our study of the differential calculus. Thank you very much.